today it's actually to study some of the Kotlin features and how they compile and what would be some performance. I'm actually a performance guy. I'm really keen on performance topics, so it will be performance in this talk. More things about me. I work as a software architect in RBI in Vienna. I'm also conducting courses. I'm technical trainer. So if you need some of this software architecture and Java performance and tuning, I might be your guy. Also, I write articles on my blog. All of them are either performance, either software architecture, and also some of them are published by InfoQ. Also, I attend conferences, I'm a speaker, and all these kind of things. What is the content for today? We will start with a bit of Kotlin introduction. Since you are almost familiar with Kotlin, I might skip or go quite quickly through the introduction, because what is a matter of interest is actually starting with the null safety and string interpolation, classes. All of these features might be interesting for you. So, what is Kotlin? Very briefly, it's actually a closed platform, statically typed, general purpose programming language, and it's fully interoperable with Java, which means actually the code that you write in Java also compiles to bytecode. So you use the same virtual machine to run it. And from Kotlin, you can call Java. That's a big advantage. In terms of history, when Kotlin came up, it was initially announced by JetBrains in 2011. Then in 2016, after a few years, they released the first version, version 1. And then I think this is the biggest event in the Kotlin world. In 2017, Google adopted Kotlin because the shape was so good in that moment. So starting Android Studio 3.0, you have the possibility to write mobile applications in Kotlin. And also the backend could be Kotlin as well. We have in a department some teams that are using Kotlin. And also we thought to use Kotlin for microservices. So it would be also something interesting for you out of this talk. In 2017, they released version 1.2. And recently, the current version is 1.3. You might wonder why Kotlin. Why you should use Kotlin? Because you are probably proficient in Java. The secret is, as Andrew Breslav said, it's a modern language. Java, you know Java, but as you will see today, the Kotlin provides you some features. And one of the most important features is because the syntax is more concise, which means actually you write less code with Kotlin because it benefits of a new features. The last one is rich features. What means these rich features? They took some of the features from C#, from Swift, from Groovy, from JavaScript, and they added those features in Groovy to create a modern language. And it's also safe, implicitly safe, which means actually you don't be surprised of null pointer exceptions, for example, and it's fully interoperable. So once you write it, you compile down to bytecode, and then you can run it. So it's very, very flexible. TOB, which is actually ranking based on the search indexes. TOB uses the Google, Bing, Yahoo search indexes, classifies Kotlin in March 2019 on the spot 39. I would say it's not very bad, even if it is 39, because Kotlin is quite a modern. It was just released a few years ago, and the trend is increasing. And you will see in these statistics other JVM languages like Groovy, Scala, and Clojure. So it's actually above Clojure. And RedMonk uses Stack Overflow and GitHub tags in order to rank the programming languages. And this it's a bit cluttered, but you see Kotlin over there. So I would say it has a good spot. Being such new language, it has a good spot. What makes Kotlin so flexible? It offers you multiple options. You write Kotlin, the source, initially you write it in a sort of KT file, and it compiles to the bytecode, and you can write the bytecode either in the JVM, whatever hotspot, what JVM you have, or for Android, you can use Darvik or ART, or they are using LLVM project, actually, and you can compile directly to native code. Or if you are a JavaScript guy, you can transpile to JavaScript. So it offers you a lot of possibilities. However, today we will speak about the right branch, for example, bytecode and the JVM. This is our aim for today. So the first topic is null safety. What is so wonderful in Kotlin is implicitly they segregated the two types of references. We have, for example, non-nullable references, which are implicit, and references which might be null. So let's tackle the first case, references which are not nullable implicitly. How you can declare them? First, you just say var, the name of the variable, column, the type, and the value. Or if you don't know the value implicitly at the moment you declare that, you can use the late initializer, which means you tell the compiler you don't have a null value, but you will initialize that value later on. And the reading, it's quite easy. So you just say read something. So let's take an example. Let's suppose you have this string, which is assigned to the constant conference. And you say, I want to compute the length of the string. What Kotlin does, because the compiler, Kotlin compiler, it's sure the reference might not be null, it doesn't do any change, actually, because it is sure that you have initialized the value not null, and the value it's not null. By the way, the bottom part, the bottom blue one, is after Kotlin compiler kicks in. So it's the generated code, and in the upper part, the white part, it's the initial code that I wrote. So this is the convention for the next slides in the talk. And now let's see, because in not all the cases you know how to initialize it in advance, right? But you still want to be not nullable. And in this case, they provide you this late init keyword. And you declare it on the first row, then you might have or you might not have the initialized variable, and then the last one you say, hey, I want to read it, I want to compute the length out of that variable. And remember, we said that Kotlin, it implicitly ensures this null safety, and what Kotlin compiler adds is this kind of check. It's an explicit not null check, and it says, if that one is null, throw an exception, and that one it's a runtime exception. Otherwise, give me the length of it. Because Kotlin compiler doesn't know. You tell him, I want this to be not null, but I'm not sure, and you might have forgotten to initialize it in the middle. So that's why, just to prevent this case, it inserts the check. So this is in terms of nullable references. For not nullable references, if you want to have a reference to a null, you can use the question mark to declare it, and later, in order to read it, you can use the safety operator, which is the question mark, or you can use the double bang operator or double exclamation mark. If you are a null pointer exception guy, who is a null pointer exception lover in the audience? So nobody. Okay, don't use that double bang then. Use the null safety operator. Let's see how they works under the hood. So first of all, I have declared that string, and I tell the compiler by that question mark, hey, this reference might hold references to null, right? And then I say, give me the length of it. And the length, I am using again the null safety operator. What compiler does? The Kotlin compiler checks explicitly if it is null. If it is null, returns the null, otherwise returns the length. But you don't have a null pointer exception. You just have a null, which is different. So you don't have exception, but you have the null returned. Or if you want a null pointer exception, using the double bang operator, it's the classical way. It checks if it is null and add that intrinsics, which, by the way, it's like you are throwing a null pointer exception in the code. So it's the old way of going this. By the way, you don't have to take pictures. Everything I already published on my website, and the code for the benchmark is already on the GitHub. At the end of the talk, I'll send you the references, so you will take everything at home. And then it's time for a benchmark, right? Because I said in the beginning, I'm more a performance guy, and I'm interested in some performance figures. So let's see the benchmark. The benchmark, I did 3 tests. The first one is not null. So actually, I have a string which is not null, and I initialize it to a conference. I said .length. So actually, it's not null. So the compiler is sure. The second one, it's a late init. Again, I've got the length out of it. And the last one, be careful, it's a nullable reference, and I want the length out of that nullable reference. But during the runtime, all of these are initialized to the conference. So during the runtime, there is no null that might be thrown, and I want to return the length out of it. Who thinks the first one is faster? Or who thinks there is a difference in performance between these? Yep. And who thinks there is no difference? I suppose the rest. OK, let's see the figure. So the figures looks like this. In case of not null late init, you can see there the figures are almost there. By the way, that is average time, which means nanoseconds per operation, which means, of course, lower the better. And you can see the last one, it's a bit bigger. It's 1 nanosecond. You might say it's not a big difference, but it's still a difference. What happens? Because the code is almost the same, right? Except the last one was a nullable reference. And out of it, I get the length. This is the trick, actually. So first, you had that 3 functions, right? And because the last one was a not nullable reference, the Kotlin compiler, the last row here, cannot map it to an int, actually, right? So it's still integer in the signature of the method. And because of that, right? So first you call, say, hey, give me the string, and then you check, because it's a late initialized field, you check for if it is null, return the length, and then the length is int. It's a primitive. However, you should return an integer. And here it's the thing. You suffer of the boxing effect. Boxing effect which affects performance, actually. Because you told initially the compiler, I might have a reference that might be null. So the Kotlin compiler cannot map it to a primitive. And this is a trick you should take into consideration. So better keep that in mind. Because if you use these nullable references for primitive wrappers, Kotlin compiler cannot optimize by using the primitives under the hood. So they keep them as wrappers. However, if you are sure that if it is not a nullable reference, yes, under the hood primitives are used. So this boxing effect causes a bit of penalty, because even if they are cached into the integer cache, it's still a delay during the runtime. This is actually what I really like in Kotlin. They added Elvis Operator. It's called Elvis because it's very similar to Elvis' face plus his haircut, right? So it's a question mark and column. And the Elvis Operator, are you familiar with Elvis Operator? Yeah, the rest are Java guys, that's why. So actually in Java, we don't have yet an Elvis operator. What does Elvis operator? It actually checks if the left operand is true. And if the left operand is true, it returns it. Otherwise, it returns the left operand. In our case, it evaluates this aggregates of objects. So it goes through from outer via nested and then inner, gets the inner value in case nothing is null, and returns the value. Otherwise, if, for example, a nested reference it's null, returns the custom value. In Java, how would look such code? Even if else, if else, if else. Other you might have used optional, because there is no such compact and concise way. That's why I was saying Kotlin has a quite compact and nice syntax. However, under the hood, how it looks like. So after you compile and decompile, it looks like this. So the language, it's this syntactic sugar, but under the hood there are a lot of null checks. So we check if the outer is null, if the inner is null, if the nested is null, and gets the value. And in case something is invalidated, it returns the custom value. So nothing magic. So I would say it's very, it compiles in a more handy way for the just-in-time compiler to kick in this optimization. Do you have an idea why it's compiled like this and why maybe not using the optional? Because of course you can write the same syntax with optionals in Java 8, right? The problem with optionals, I also have a post on this on my blog site, it's a bit slower. Of course, it's a bit rudimentary to write if-else with null checks, but it's faster. Why? Because compiler loves this kind of null checks. The just-in-time compiler really optimizes better the code in such way. And I did a comparison between Elvis Operator and Java optional, and as you can see, the Elvis Operator, it's a better. Of course, it's still little better, but it might differ from context to context. But in essence, the manual if-else, when you check the nulls, this might be better. And here is the proof. You might not have expected assembly in such Kotlin talk. However, let's make the things more challenging. This is the real proof what happens down to the hardware. And really, when you do benchmark profiling, go under the hood, because otherwise you don't really understand what happens. And here is the Kotlin-generated assembly code. And you can see clearly that there is no explicit null check. That's why in the previous benchmark, the Elvis operator was faster. Because, as I was told you, the compiler loves really these null checks. It relies on some aggressive optimizations, and it compiles down to a very optimal assembly. Good. String interpolation. What is string interpolation? This is another feature that I liked in Kotlin. Actually, you have a literal, and inside that literal, you have some, for example, some placeholders that must be replaced. And it's quite compact and nice code. In Java, there is no such way. You can use string format or string appender, but still, it's not one line and very clearly understandable. And also, as you can see, the first line, you can add some expressions in that interpolation example. However, how it compiles, it's still based on string concatenation. So the old-fashioned way of dealing with this. So Kotlin compiler replaces that string interpolation expressions by using this ++++. Under the hood, you might know already, this is what Java until JDK 9 did. Everything is based on string builder, right? So they create a string builder, and they are using this append, just to save the number of instances allocated. Just to conclude based on this, I would say Kotlin uses, for string interpolation, they are using string builder. However, I did some benchmark. My benchmark measures the throughput of each method, actually, the response time of each method. And I measured in case of Kotlin and in case of Java. Which one do you think was faster? In Java, we don't have string interpolation. However, I took the same example like here, and I was using plus operator. So I was using shape plus area is plus length multiplied by width plus unit, something like this. Which one do you think it's better? The Java, right? A real Java lover. And you're right, Java was better. Actually, Kotlin was also slower, as is written there. And may you guess why Java was? It's exactly the same source code. If you compile with Kotlin, Kotlin has the main line. It's Java 8 bytecode compatible, and if you compile, for example, with Java 11 or 12, the last one recently released, Java is faster. Any guesses? It's because starting JDK 9, Java for this string concatenation doesn't use string builder anymore. They completely switch. They switch to an invoke dynamic. So every time you create these strings which are appended, it's not string builder anymore. It was as it was prior JDK 9. Starting JDK 9, they moved to this invoke dynamic, and under the hood, the default strategy it's using a byte array. So it's much more performant than the old-fashioned way. And in this case, this is the JEP. It's called Indify, string concatenation, and this is the JEP actually that brought that feature at the bytecode level. So they changed the bytecode a bit. And this is another, let's say, takeaway for you, because Kotlin compiles, the main line is Java 8. You can also switch the target to create Java 6 bytecode. You don't benefit of latest bytecode improvements, especially this one, Indify, string concatenation, and there are two others in JDK 11. One is for the constant dynamic, and another one is for nested classes. So in these particular cases, if you write code in Kotlin and the same code in Java, or very, very similar way, Java is better because you benefit of this bytecode enhancement. And this is another takeaway. Data classes. In Kotlin, it's quite short and it's quite concise. This is how you declare a data class, a class. First, let's take the class. It's just one line, and inside it, you can set all the fields. And for example, the middle field, the city, it might be null. So just one line, right? So it's very, you get rid of all those weird getters, headers, equals, hash code methods that you always have to maintain. Refactor something, you refactor also the getter and the setter. So it's a bit bothering us, right? But what happens in Kotlin is that Kotlin generates, the Kotlin compiler automatically generates the fields, the getter, and the constructor. It's very similar to what Lombok project does, if you want. So you declare just one line, and under the hood, the bytecode contains those three. And if you look over the generated code, it has the fields, and it has some annotations because name cannot be null, the city, which is nullable, and here, because initially I was declared here as an int, like an object, and because it is not nullable, it was converted to a primitive, actually. And this is what I was told you before. This kind of wrappers for primitives, if they are not null, they are desugared into primitives. Getters, nothing special, and the constructor itself, the constructor just checks if the name it's null. If it is null, throws an exception. If it is not null, creates the instance. Simple. But imagine you want more than that, because sometimes you want, for example, equals, you want hash code, you want other methods, right? And for that, you can prepend the signature of the class with data. And in this case, if it is a data class, Kotlin generates a lot of methods for you, besides the getters, constructor, toString equals, and hash code. So that one, those ones are generated only if the class is a data class. It creates this component function, copy and synthetic copy. And these are very useful. So let's look into the pink ones, for example, the component function, the copy, and the synthetic copy, to see how it looks like. For each field, Kotlin compiler adds a component method, which actually returns that field. And this is used in case of destructuring declarations. Have you heard about destructuring declarations? Okay, we will talk in a way. So these are used for destruction declarations. I will tell you what it means. And then you have the copy method, which actually receives the name and the rating. It checks if the name is not null, and then creates the instance. And then it creates a synthetic method. What is this synthetic method? This is an additional method the user haven't declared explicitly, but it's used to do some workarounds. And here the workaround is every time you call the copy method with number of fields which is less than the number you have declared. For example, you can call it with 1, 2, or 1 each of them, or without anything. It calls the synthetic method. And the trick is here. So you call the synthetic method, it receives the target reference, which is the talk, the instance itself. Then are all the fields, name and rating. And here is the trick. That var free, it's actually a placeholder. And it uses the placeholder and the bitwise operation to detect if you call the copy with null or without a null. So if you call the copy with something which is not null, which is null, sorry, it takes the value from the instance. For example, name equals var 0.name. And the same for rating. So it creates the name and the rating, and then dispatches the call to the copy. Let's take an example. It would be easier. So you have this talk, the instance one, and then you want to create a copy. And in this case, the copy method, it's called the explicit one, which actually takes the argument C++ and the rating and creates a new shallow copy out of it. However, you can also call the copy, the upper part, you can call without any explicit argument or without one, whatever that one is. And in this case, for the last free copy, it's the default one called, and as I was told you, the trick, the placeholder, it's this var free. So based on this var free, it detects if you injected the argument which overrides the one which belongs to the talk, it takes that into account. Otherwise, it uses the one from the talk. It's quite a simple trick. So this is how it handles this kind of, let's say, default arguments for copying and creating shallow instances. And I was mentioning before about destructuring declarations. What it means actually, in this line, you can say, you can declare 2 variables and you assign those variables to an instance. A bit weird at the first glance, right? What it does under the hood, actually, the Kotlin compiler takes each of these variables and assign to a component function, the component function that I was mentioning about. So by the order you declare them here, the Kotlin compiler creates this. So of course the order matters because if you declare first rating and then name, you will have the rating in rating the value of name, because Kotlin compiler doesn't do any such analogy. However, by ordering them and using this component, implicitly you have the values spread out into the variables. And also the nice thing is you can also have these destructuring declarations to assign them with a function return, for example. Instead of getting the value out of that function and say get, in one line you can have everything set in those variables. So it's really nice and concise code. Extension functions. The question is, what are these extension functions? Imagine you have a class which is a final class, right? Like we have in Java, a string or integer. But you want to create your own method which belongs to that class. It's not possible via useful mechanism, via quickest mechanisms. You might do that, but a bit in nasty ways. However, Kotlin solves this problem, and the syntax for that is function, you can say the receiver type, dot function name, and then the return type and the body of the function. Let's take an example. So for example, I want to create an extension of string class, and that extension, it's named wrap, which does actually wraps the argument receive, wraps it into these angle brackets. This is what I'm doing. So actually it's an extension. How it is called? Like this. So you have a normal string dot wrap. It's quite nice, right? What the compiler does, Kotlin compiler, it adds static methods. So all of these extension functions are desugared into static methods. And then when you call it, like for example this line, the string.wrap, it's called like this. It's like you declare a static method and call it explicitly. This is no trick around it. But it's quite useful because you can declare extension functions for integer, for string, for whatever final classes you might found or you might need in your application. Default arguments. Let's suppose you have that method signature, right? And in some cases, you might not need all the parameters. Or in some cases, you might need some default values for those parameters. And it's very nice. Java doesn't have that. C++, for example, have this option, and it's quite useful because it prevents you to write by overloading again and again new methods. So you just create one with default. And how it looks like, for example, you have the expression, and only the first parameter out of the expression, the value, it's a mandatory one. However, I can call the expression with factor and delta as being optional. And if they are optional, the default values are used. For example, 0 and 1. But you need to specify in the method signature. What it does, compiler, very similar to the copy method, it adds that default expression $default, which is another syntactic method, which actually acts on the same principle as for the copy. So first it takes the instance, it takes all the parameters, value, factory, and delta, and then the var4 is the placeholder, and based on how you call the method, it uses that var4 some bitwise operation and detects if you call it with a non-default or if you call it with a default. So this is what it does actually. And then if after it sets the values, it dispatches to the normal expression method. How it looks like, for example, if you call the first one, if you call expression, and in this call you are using two default arguments, right? Because factor and delta have assigned to 1 and 0. The second call of expression received the factor of 2, but still I'm using delta as default, which is to 0 set implicitly. And the last one, it's actually 8 factor of 2 delta of 1, and in this case nothing is default. I call the method with explicit arguments, and in this case the normal expression method is called. However, if you have some defaults and you call with less number of parameters that you have declared, you have such trick where you use the syntactic method, and based on var4 and the bitwise operation, it detects what you should to properly assign the variables. And yeah, and then I did a benchmark as well. Actually, this benchmark, what it measures, it only measures the cost of that syntactic method. Only that's it. Because in the first case, I have an expression which actually uses only the value, and the other two are optional, are set to default. And the second one uses only one default argument, and the last one has no default. And as I was saying, I want to measure only the overhead of these syntactic methods, because you might think it's a bit of overhead. However, it might not be such difference. Default two arguments, it's around 2.4 nanoseconds. The other default one, it's still 2.4, and no default, it's still 2.8. Do you might guess why the last one it's a bit slower? It's because actually all of are optimized in the same way. So everything is optimized very nicely. However, when you call it with not default, there are additional CPU instructions because you need to compute a multiplication plus an addition, and it needs extra cycles. That's only the reason, and you have there the proof. However, for example, in case of 2 default arguments, the compiler realizes, oops, it's a multiplication plus 1 and an addition by 0, right? It removes that. So it returns only the value. And the same story for the middle one for default 1 argument. But in essence, just-in-time compiler, C2, I was using here, realizes and really optimizes. So I would say no extra overhead due to these synthetic methods on this benchmark. Don't take it for granted in all, but in this benchmark there was no. Inlining, it's a quite interesting and a lot to discuss here. However, before going into the inlining, let's tell you a bit about high-order functions. In Kotlin, there is this notion of high-order function. What it means, a high-order function? It's actually a function which might take a parameter another function or might return another function. And there is the syntax. So you have the high-order function, and the second one, it's a parameter which actually takes another function. And these functions, high-order functions, are actually represented by function types. What is a function type? It's actually like this. It contains the type, the input parameter, and the return type. Everything is represented by these function types. And if you want an example of that, let's suppose you want to create the sum of squares, right? So creating the sum of squares from 1 to max, and then you pass in to the method a square which is another function. And in the body, you iterate through them, and you call that function which was received in the body. If you, for example, have a look how it works, it creates actually, it changes a bit the signature of the method because, of course, you pass it the function, and at the bytecode level, there is no such notion by using function 1. What is this function 1? How it works? It's a very similar principle with functional interfaces. Actually, it creates an instance of this guy, and inside the invoke method, it dispatches the call to square. This is how it handles. So every time you call this square, and here it's actually called a func.invoke, which actually dispatches the call to square. I have it better here. So this is the decompiled shape of that. So it's function at runtime. Every time you call the square, it's actually a dispatch via the invoke method, which belongs to the interface. And maybe curious or surprisingly or not, in Kotlin there are up to function 22. This is function 1. It takes 1, returns 1, but they declare up to 22 such options. So you have really a lot of options. You can play with a lot of parameters. I'm not sure who's so crazy, but yeah, you have those there. Okay, good. Then I took this very short benchmark, and what I did, I just tried to compute the sum of squares of elements from 1 to 1 million. And what are the figures? You can see I measured the average, I measured the allocation rate, I measured the GC, garbage collector count, and I measured the GC time. But it looks a bit weird because you don't have any reference. So if your colleague gives you such figures, you don't know if they are good or bad. However, there is a bit of smell, and the smell is the number of allocation rates and the GC count. It's a bit too much, right? So as you can see, the allocation rate was 4,300 megabytes per second just to compute the sum of squares. Isn't that too much? Of course, it creates a lot of garbage. How you can improve the performance? Inlining. What Kotlin offers as a language feature is the inlining keyword. It's the explicit inlining keyword. If you have programmed in C, there was also an inlining keyword. So what it does, actually, you just prefix the method with inlining, just like that, right? You don't change anything in the body. Only the signature is changed by that inlining. Everything, it stays the same, and then you redo the benchmarks. And on the right side, you see only adding inlining, we got way better figures. Like, for example, the GC count and the GC time were 0. Both of them, the average, it's also 0.3 milliseconds per operation. What happened, actually, by using the inlining, in this case, we got rid of that functional instance during the runtime. And because of that functional instance during the runtime, there were a lot of garbage, a lot of objects created which add a pressure for the GC. So because of that inlining in the signature of the method, it got inlined in the call side, in the caller. Actually, it got inlined the higher order function, plus we got rid of the lambda, because actually the sum, it was a lambda. So by using this inlining, we got rid of two things. The lambda overhead plus the callee was inlined into the caller, the call side. So it's quite interesting. And if you are searching through the Kotlin JDK, you will see a lot of such short methods are prefixed by inlining. I wouldn't advise you to do that, because I've got this question, okay, let's do inlining for everything. No, don't do that, because it's tricky. Inlining, if you attended the Chris Tallinger talk from Twitter, inlining, it's good, but you really need to check on your size if it fits your context or not. In some cases, you might get even worse results. The next interesting case, it was about polymorphism. Right, and what is about it? Suppose you have this hierarchy of polymorphic classes. You have a base class, which is a CMAT, and you have 4 implementations, ELG1, 2, 3, 4. They are it's a synthetic example anyway. And then you have a method which is inlined. It's called inline fun compute, which can receive actually the base, the CMAT, but during the runtime it receives any implementation actually, right? So it can receive during the runtime every possible implementation. So in essence, it could receive ELG1, 2, 3, and 4. If I want to step a bit, in theory, this kind of calls are called megamorphic calls. It's megamorphic because it is called with more than 2 instances. So if it is called with 1 instance, it's monomorphic, 2 instances bimorphic, and starting with the 3rd possible implementation is called megamorphic. For example, this compute, if I have during the runtime only ELG1 instance, it becomes monomorphic, right? So if I have ELG1 and ELG2, they are bimorphic. It becomes bimorphic. And starting with ELG3, inclusively ELG4, it's megamorphic. Why is this? Because it matters. Just-in-time compilers had some limitations in optimizing starting with the 3rd implementation. And what I did, just for to get a bit of fun with this benchmark, I've created 4 cases for a monomorphic call. As I was telling you, is just 1 implementation. This is the monomorphic. Bimorphic, 2 implementations, and megamorphic 3 and megamorphic 4. There are 3 and 4 possible implementations during the runtime. So this was the benchmark, and I tested with Kotlin and with Java. By the way, a bit of difference, because in Kotlin I was using the inlining keyword I was talking about. And there are a lot of figures just to spot it out. In case of bimorphic 3 and 4, for Java, it's not so good as in Kotlin. In Kotlin, I was using the inlining in Java, we don't have such explicit inlining. Nevertheless, it turned out that at the end, Java was a bit slower. And was slower because this is a bit tricky thing. This is the optimization happening in the Java. What Java does, I took here the megamorphic 3 call example. It just dispatches to virtual calls. So in order to execute the compute, it does virtual calls. So it does call. The first call is here, and it creates this. The second is here, and the fourth is here. So it cannot do any optimization because just-in-time compiler is quite limited, starting with a third possible implementation. However, in Kotlin, because I was explicitly using the inlining keyword, Kotlin didn't trigger any such call. So it was everything, I would say, inlined and computed like a normal arithmetical operation. That's why you also have a better performance in terms of Kotlin. Just to conclude this case, explicit inlining in Kotlin pays off in performance, especially at megamorphic call sites. And to be honest, this is probably the single case you should optimize in advance your code. If you see there is a megamorphic call site, do explicit inlining. Otherwise, don't do explicit inlining because you might end up stressing the compiler and making the footprint of the code size quite bigger during the runtime. But if you see that during the runtime that is a megamorphic, and if you are not using Graal, to be honest, because if you test the same with Graal, just-in-time compiler, Graal is able to do this kind of optimization. So in Graal, you don't need the explicit keyword. However, if you are not using Graal VM, neither Graal just-in-time compiler, use this inlining keyword. This is the only trick. More details, I also wrote a blog post on this. I explain in more details what happens. The idea is this one, to stick with this inlining where it makes sense. Conclusion out of my talk, we went through a lot of cases. String interpolation was a bit tricky. It was a bit slower due to the bytecode sequence emitted. And this is because the Kotlin mainline is still Java 8. However, all the others were better. However, be very careful with inlining because, as I said, it could be your friend, but it can turn out into a real enemy for the compiler. Thank you so much for your attention for, I would say, a bit of compiler / under the hood Kotlin talk. And if you are interested in further resources, everything is public. Thanks a lot.